Okay, so right now looking at this video, you might be experiencing a little bit of deja vu, but really it's not. What I've done is I'm showing you the work that we had done back whenever we were doing conservation of energy. And I said that in that video that we had multiple approaches to solving for the speed of the ball as it rolls down the ramp, and that the energy approach is usually what most people would go for in any problem because it doesn't involve vectors, and so it's generally a much easier problem to solve, provided you're solving for something that energy can give you. So for example, you typically would not use energy to determine how much time it takes for something to occur. It's possible through the use of power, but it's not something that you would typically attempt to do. So basically what we were doing in this video, or in that video, the one dealing with energy, is we said, look, we could put the axis of rotation at the center of the ball, or at the center of the rolling object, or we could put it at the point of contact, and that each one of those has its advantages, but our focus was what we see here, and that relates to whether or not to include translational kinetic energy. So that was the big thing in that video. So one approach, we had the axis of rotation was in motion because it was at the center of the ball for the instant in which we were studying the object when we diagrammed it. And that led us to this expression of 10/7 gy was equal to v squared. And then we went on to do a less traditional approach where we did not need to use translational kinetic energy because we used the point of contact as our axis of rotation. And then we had to use the parallel axis theorem in order to determine what the new moment of inertia was. But in the end, in the final analysis, we got the exact same expression. V squared is equal to 10/7 gy initial, or the height of the ramp itself, the distance that it rolled vertically through. So I want to build on that now so that you can see that the four perspectives approach that I've been teaching you for the past year and a half is a valid way of approaching problem solving. That it's just four different perspectives for analyzing a particular interaction, some type of phenomena. So what we're going to do in this video is we're going to look at using forces as our starting point, and then we're going to show that v squared is equal to 10/7 gy initial, or gh, the height through which the ball is going to roll. So this video is probably going to be just a little bit longer than normal, because I have to show it to you twice for the same reason that I had to show it to you twice when we did the energy approach. Because especially with this particular problem, when you go out on the internet with university level physics, it is not uncommon to see the point of contact as the axis of rotation. Okay, so the first thing that I want to do in this problem is to just review a couple of things about rolling without slipping. And I'm not going to spend a lot of time on this. We did it rather extensively last year, so this is just meant to be a review of the most salient points associated with rolling without slipping. And so we have some no slip conditions. And if a rolling object is not slipping, we know that VCM is going to be equal to r omega, where r is the radius of the disk or the ball, whatever's rolling. ACM is equal to r alpha, and the distance through which it rolls, d, is the same thing as the arc length, or s, is equal to r theta. So basically we're just looking at the bridge equations here. Now, the other thing that I want to remind you of is that when you have this rolling object, that at the point of contact, v translational is equal to 0. If the object is moving to the right, so we're just going to say generally the object is moving to the right, at the center of mass, V is just equal to, I'm going to call it VCM. And at the top of the wheel, we're going to have 2 VCM. And then finally, the last thing that I want to mention is that the speed for the rim of the wheel relative to the center of mass, using the center mass as the axis of rotation, all we're looking at is how fast it's moving. We would say that the edge is moving with a speed of VCM. Notice I didn't call it velocity, I just called it speed. So those are the important properties of rolling that you just need to keep in mind for rolling without slipping scenarios. So let's write this down. VCM is equal to V tangential. That's how we would have stated that last year. Okay, so what we're going to do now is we're going to label a few things associated with this scenario. We're going to label the forces and the wheel itself. And we have, first of all, that the ball, I'm sorry, this is a rolling ball, that the ball does have a radius of r, and we want to diagram the forces which are on this ball. This is going to be really important to our analysis. Okay, so remember that when we're doing rotation, you always want to make sure that the force originates on the diagram at the actual point of contact. Let's figure out what forces are acting on the ball. Now remember that all forces are contact forces except for gravity. In this case, we have one touch, which means we have a maximum of 2 forces due to contact, and then we have the non-contact force of gravity. So let's label the non-contact force first, because that's a really easy one. It starts at the center, and of course it's going to point straight down. So there's the force of gravity. Now I'm not necessarily going to draw this to scale. But that one there is the force of gravity. Now, because of the touch, we know that there are 2 possible forces due to any one touch of 2 solids coming together. One will be the normal force, which always exists. And the normal force is always going to be perpendicular to the surface. So that means we're going to go from the point of contact, and it's going to extend through the center of mass of the rolling ball. So the normal force is going to be that. And then finally, we have one more force which acts parallel to the surface, and sometimes it exists, sometimes it does not. Now, because we have rolling, it must exist, because if this were a completely frictionless surface, there would be no force causing the ball to roll. And of course, that parallel force is the force of friction, and that is going to have to point up the ramp in order to cause the ball to rotate in that counterclockwise direction as it goes down the ramp. Okay, so we have the normal force, we have the force of friction, and then we have the force of gravity. Okay, now let's go ahead and start to analyze this. When we analyze it, there are 2 possible or 2 obvious points for the axis of rotation. One is going to be through the center of mass, and the other is going to be through the point of contact. At the university level, the point of contact seems to be the preferred location for the center of mass. I don't honestly know why. I think it's probably the one that most students get tripped up on, because it's not what you normally think of as your axis of rotation. But we can select any axis of rotation and make it work. That's the nature of rotation. So what we're going to do first is use the center of mass as our axis of rotation. And for this, we would just write tau net is equal to I alpha, right? No surprises there. And we have 1, 2, 3 possible forces. So we'll just write it out. We have the torque due to gravity plus the torque due to the normal force plus the torque due to friction is equal to I alpha. Let's see if we can eliminate any of these forces, because that's going to be an awful lot of writing. All right, so the torque due to gravity, we're using the axis of rotation we're using the center of mass as our axis of rotation. And because we're using the center of mass as our axis of rotation, torque being defined as R times F times the sine of phi, we can see that the distance between the point of application and the axis of rotation is 0, which means we're not going to have a torque due to gravity. That will be 0. Now, when we talk about the normal force is pointing parallel to R. Remember that R is going to go from the axis of rotation, so if I just draw it up here, R would be going in this direction, but the normal force is going to be exactly parallel to that, going in that direction, and therefore we get phi is equal to 180 degrees, and the sine of 180 is going to be 0. And therefore that means we lose torque due to the normal force. Okay, so the only torque we have acting is going to be the torque due to friction, which becomes R times the force of friction times the sine of phi is equal to, for a sphere, I is going to be equal to 2/5 mr squared times alpha. All right, now, a couple of things. R for friction is going to be the distance from the center of mass to the edge, which just becomes capital R. And then we have the force of friction, and the sine of phi, we can clearly see that this is going to be a 90-degree angle here. And because that's a 90-degree angle, we know it's just going to be 1. Sine of 90 is equal to 1. Then we have 2/5 mr squared alpha. Now we're trying to determine the acceleration of the sphere, of the ball, so that we can then calculate the final velocity when it reaches the bottom of the ramp. Okay, so that means we have to get out of angular units and into translational units. So alpha, using the bridge equations, just becomes A over R, and now we can cancel out some stuff. One of these R's cancels with that. This R cancels with that. Okay, now at this juncture, you're going to be tempted to want to try to substitute mu times the normal force for friction. But this is going to be one of those cases that you don't want to do that. And if you were doing this problem on your own, you would do it anyways, because you wouldn't have that experience to know that this is not a good idea. And that's okay. You know, that's part of learning physics. So we're just going to leave it like this for now. The force of friction is equal to 2/5 ma. That's what the force of friction is going to be. Now, something to take note of here, that this is not necessarily equal to mu times the normal force. It's only the force necessary to cause the ball to rotate. So you may have a very, very large normal force that's going to be something much greater than the 2/5 ma. But you only need 2/5 ma in order to cause the rotation. So that's a really important distinction, because this rolling friction, it's a type of static friction, right? And static friction, we know, is less than or equal to mu times the normal force. So we're going to be somewhere less than the maximum that we get out of that. So just keep that in mind. All right, now this ball is translating through space, so that means we're going to have to do F net is equal to ma. And for this one, we want to be a little careful. The ball is only translating parallel to the ramp. And if it's only translating parallel to the ramp, only forces that are parallel to the ramp will be affecting the acceleration. So we're going to write those forces. What are they? Well, look carefully and you'll see that we've done this before. This is a ramp problem. We have the force of gravity points straight down, but the force of gravity has components which are perpendicular to the ramp and parallel to the ramp. So basically what that means is this angle theta here is the same angle here, and that the parallel component of gravity is what's causing the ball to roll down the ramp. And so we have the force of friction is pointing up the ramp, that's a positive direction, minus Fg parallel is equal to m times a. But now the way I have set this up, we have the ball rolling down the ramp, so that's going to make this acceleration negative. So we can write this, we know Fg parallel from our study of ramps before is going to become mg sine of theta minus the force of friction is equal to ma. So basically I just got rid of that negative sign by swapping sides. All right, now this is why we did not want to try to solve this out with mu times the normal force, because we're going to substitute 2/5 ma for friction. So we get mg sine of theta minus 2/5 ma is equal to ma. Now we can see that the masses are going to cancel, and we're going to now solve this for acceleration. So we'll move this 2/5 ma or 2/5 a to the other side, and we'll get g sine theta is equal to a plus 2/5 a. Now 1a is the same thing as 5/5, so we get 7/5 a is equal to g sine theta. So a is equal to 5/7 g sine of theta. All right, so that's the actual acceleration of the ball. So now how do we determine what the velocity of the ball is going to be at the bottom of the ramp? So let's go ahead and add a few more conditions to make this possible. So the ball starts at the top of the ramp up here. It goes to the bottom of the ramp, and when it does, it's going to fall through a height of h, just like we had in the previous example. And so it's going to roll through some distance d. Okay, so we have, because we don't know time, we're going to use v final squared is equal to v initial squared plus 2ad. V initial is 0 because it starts from rest. And so we get v final squared is equal to 2 times 5/7 g sine of theta times d. So this is going to give us 10/7 g sine theta times d. Now we still have to work on d a little bit, and we know that y is equal to d sine of theta. So d is equal to y over sine of theta. So finally we get our answer. V final squared is equal to 10/7 g sine theta times y over sine of theta. And the sine theta cancels out of it, and we're left with v final squared is equal to 10/7 g y, which is exactly what we got whenever we were using conservation of energy. So you can see that this was a lot more work in order to get to that. But the point is, if this makes more sense to you and you're more comfortable using Newton's second law, then by all means you can use Newton's second law to get to the final velocity. You just have to know that you're going to use forces and then kinematics in order to achieve that. Okay, now the last thing I want to do is go through the example where we use the point of contact as our axis of rotation. Okay, so the problem is still going to start out basically the same. We're still going to write tau net is equal to I alpha, and we still have the torque due to the normal force, the torque due to gravity, and then the torque due to friction is equal to I alpha. Now in this example, with our point of contact being our axis of rotation, this is what we have to pay attention to. R for the normal force is going to be 0 because it originates at the point of contact. R for the friction force is going to be 0 because it originates at the point of contact. And so the only force which is going to cause an acceleration is going to be the force of gravity. So gravity causes a torque, but nothing else. So we can make the torque due to the normal go to the 0 and the torque due to friction go to 0. And that's because for each of these, R is equal to 0. Now, the torque due to gravity is equal to R gravity, F gravity, sine of phi gravity is equal to I alpha. Okay, so now again, we have to be a little bit careful here. We already know that the component of gravity which is going to cause acceleration is just going to be the component which is parallel to the ramp. We know FG points straight down, there's a perpendicular component, and then there's a parallel component. And we're only interested in the parallel component. Parallel component points that way. FG parallel is equal to FG sine of theta. Okay, so we're only using the parallel component. This component, by the way, is perpendicular to the moment arm. R goes perpendicular to the surface like that from the point of contact. And then FG parallel points parallel to the ramp like that. And so all we need is FG parallel in order to determine the torque due to gravity. So I can use the version of the expression for torque. I can say that R times F perpendicular to R is equal to I alpha, and I don't need to use the sine of anything. So that's what we're going to do. So we basically have R times FG sine of theta. Notice it's not phi. Sorry, this should be phi here. All right, we're using sine of theta is equal to I alpha. Now I'm not ready to just, move on to the next part of this. We need to do something with I. All right, now I is not going to be 2/5 mr squared. And that's because our axis of rotation is through the point of contact, which is at the edge of the sphere. So we'll have to use the parallel axis theorem to calculate I. So I is equal to ICM plus MD squared, which is 2/5 mr squared plus m, and the distance we move the axis is r, 1/2 the diameter, or r, so it becomes r squared. Therefore, I is going to be 2/5 plus 5/5 is 7/5 mr squared. Now we can make that substitution. R times FG sine of theta is equal to 7/5 mr squared, and then alpha is going to become A over R, and we get to cancel this R with that R, this r with that r. FG can be written as mg. So we have mg sine of theta is equal to 7/5 ma. And so we can cancel that mass with that mass. And you can see this is starting to shape up and look basically exactly like we had before. Okay, so we get g sine theta is equal to 7/5 times the acceleration, or the acceleration is 5/7 g sine of theta. And now we'll use kinematics to finish solving it. So we have v squared is equal to 2ad. We already know it starts from rest. So that's going to be 2 times 5/7 g sine of theta for the acceleration times d. And just like we did before, it's up here. Look up here. Okay. Just like we had before, we know that d is y over sine theta. So v squared is equal to 10/7 g y, which is exactly what we saw before. Okay, so that's it. Really long video. Sorry for that. But I think it's important for you to see how everything connects together, that it's your perspective. What do you want to use to solve a particular problem? And within any one perspective, you still have choices. So don't be discouraged just because the first way you attempt a problem doesn't seem to work for you.